In this video, we'll be going over how to find the potential energy, velocity, and kinetic energy at 3 points along a toy car track. Our givens are the mass of the car of 0.044 kilograms and gravity of 9.8 meters per second per second. We will also be given the height at the 3 points along the car's path. We'll be using three formulas: potential energy plus kinetic energy equals initial potential energy, which is true for a problem like this with a zero starting velocity. Gravitational potential energy equals mass times gravity times the height, or in other words, m times g times h. And kinetic energy equals 1/2 mass times velocity squared, or in other words, 1/2 m times v squared. In order to get the equation for velocity, we can use the three formulas to come up with a new formula. For a problem like this, we will assume that energy is conserved. This means the energy of the car at any given point is equal to the initial energy at the beginning. So we can trade off the potential energy at the beginning for kinetic energy at other points along the track. So current potential energy plus kinetic energy equals the initial potential energy. Note, some of the initial potential energy will go towards friction loss, but this will be ignored in our calculations. So now we can rearrange the formula so kinetic energy is to one side and initial potential energy minus current potential energy is on the other. Next, we can plug in the potential energy formula of mass times gravity times height. We can simplify this to be mass times gravity times the height difference equals kinetic energy. Now we have two formulas for kinetic energy. Being that kinetic energy equals kinetic energy, we can set the two formulas equal to one another. After doing some rearranging of formulas and simplification, we get that velocity equals the square root of 2 times gravity times the height difference from the beginning. Using the formulas, let's find the potential energy at point 1. We can use the formula mass times gravity times height equals potential energy. After plugging in our mass of the car of 0.044 kilograms, an acceleration due to gravity of 9.8 meters per second, and height of 0.16 meters, we get a potential energy of 0.069 joules for point 1. This, as discussed earlier, is the total energy of the system, being that there is no starting velocity, so there is no kinetic energy at this point. On to point 2. We can once again use the potential energy formula of mass times gravity times height and put in the height value of 0.04 meters. We get a potential energy of 0.017 joules. Now we can use the velocity equation we found of velocity equals the square root of 2 times gravity times the height difference, or in other words, height delta. After plugging in our height of 0.04 meters, we get a velocity of 1.53 meters per second. To find the kinetic energy, we can take the initial potential energy minus this point's potential energy. We are left with a kinetic energy of 0.052 joules. On to our third and final point. We once again use the potential energy formula of mass times gravity times height and plug in our height of 0.1 meters. We get a potential energy of 0.0431 joules. We can once again plug the height difference at this point from the initial point into the velocity formula we found. We get a velocity of 1.08 meters per second. If you are like me, you are probably curious about how fast our experimental car was. So the velocity is the displacement over time. So we will use the displacement of 0.2286 meters, which is about the length of the book. I did a frame-by-frame analysis to see how long it would take to the car to cover the distance of 0.2286 meters. I ended up with a time of 0.234 seconds. Now we can plug our displacement of 0.2286 meters and our time to cover the distance of 0.234 seconds into our velocity formula of displacement over time. We get a velocity of 0.977 meters per second. This is close to the calculated value, but may vary slightly due to us not accounting for friction. Another possibility is that the car experienced a slight elevation gain due to the track bowing over the book. And finally, my frame-by-frame analysis may be off slightly. To finish off this video, let's take the initial potential energy minus the potential energy at point 3 to get the kinetic energy. We get a kinetic energy of 0.026 joules. That concludes this video. Hopefully I earned a like, share, or subscription. If you like this video, you may enjoy one of these videos as well. Thank you for watching.